hi. Let's talk about momentum. Remember Newton's second law, F equals ma. But let's write it this way. Remember A is delta V over delta T. So this is M times V final minus V initial over delta T, or mv final minus mv initial over delta T. So this looks like we've got this quantity mv at the end and this quantity mv at the beginning that's changing. So we define this new thing called momentum as m times v. We give it the symbol P. I don't know why it's given the symbol P, it just is. So momentum by definition is the mass times velocity. This means Newton's second law can be written as this P final minus P initial, or just delta P over delta T. Now, so this idea of momentum has two fundamental uses. It has uses for when we're talking about forces, and it has uses when there are no forces. So let's look at those two cases. First, when we're dealing with forces, and in particular momentum's important when we have a very large force that acts for a very short time. That's typically called an impulsive force. So we've got force is delta P over delta T, and let's give you the example of a baseball hitting a bat. That's a very, well, you probably have a bat hitting the baseball, but that's a very large force that acts for a very short time. So here's our baseball, has a mass of 145 grams. It's moving with an initial velocity of 35 meters per second, and it's struck by a bat. And afterwards, the baseball is moving the other way, still has the same mass, has now V final of minus 40 meters per second. It's going even faster than in the opposite direction. So let's estimate the force if this collision between the bat and the ball takes an estimated time, delta T, of 0.7 milliseconds, 7/10 of a millisecond. So we've got, force is delta P over delta T is P final minus P initial over delta T. This is mv final minus mv initial over delta T. Excuse me. So this is mass 0.145. There's 145 grams, so 0.145 kilograms. V final is minus 40 meters per second. Minus mv initial, 0.145 kilograms. The initial was 35 meters a second. All over delta T is 0.7 times 10 to the minus 3 seconds. It's 10 to the minus 3 because this was milliseconds. And I've keyed all that in, and you get a very large force for this very short time of minus 1.6 times 10 to the 4th newtons. So this impulsive force, we call it, has been estimated by using this concept of momentum. So we got F as delta P over delta T. If we multiply through by delta T, we can get delta P is F delta T. And sometimes this product, F delta T, is called the impulse. and the F is called an impulsive force. So an impulsive person is someone who does something suddenly. They just, suddenly get up and, go to the mall or something. So that's an impulsive person. This is an impulsive force. It's a big force over a short time. All right. Now there's another case where momentum is of really, truly fundamental importance. And that's the case when there's no external force. Suppose there's no net external force. If this is 0, then this delta P has to be 0, no matter how small this delta T is. If this is truly 0, then this delta P is 0. This gives us a truly fundamental law, the law of conservation of momentum. It's one of the most fundamental laws you'll see in this course. This says if the net external force is 0, then the momentum before an interaction equals the momentum after. So there is an if there. Remember the if. If the net external force is 0, then the momentum before an interaction, like a collision, this is often used in collisions, an interaction equals the momentum after. Law of conservation of momentum. If the net external force is 0, then the momentum before an interaction equals the momentum after an interaction. So the momentum doesn't change. The sum, the total momentum, doesn't change. By momentum now, I mean the total momentum, the net momentum. Let me show you my example. Typical example is a collision. Suppose I have a cart moving along a track with mass M1, where M1 is 0.500 kilograms, and it's moving with V1 initial of 0.450 meters per second. Some wheels, assuming no friction, although even if there is some friction, if the collision is short enough, the momentum would be conserved right before and right after. There's another cart, M2, that's just sitting here. So M2 has a mass of 0.490 kilograms, so almost the same mass, but not quite. So this is the initial situation. Then the final situation after the collision, well, let's make it look about the same size. We've got cart M1 is moving with V1 final of almost stops, 0.12 meters per second. It was moving with some V1 initial of almost a half meter per second. Now it's going really slow, tiny little velocity, and we want to know what is the final velocity of M2. So we want to know V2 final. So notice how I'm labeling these. This is V1, the 1 means cart 1, the I means initial. This is V2, initial is 0, cart 2 was just sitting there. V1 means cart 1, final, is moving this fast. Since it's positive, it means it's going to the right. V2 is cart 2, F means final, and we want to know how fast is that. So law of conservation of momentum says is we add up all the momenta before the collision has to be what we get if we add up all the momenta after. So all the momenta before is M1, V1 initial, plus M2, V2 initial, equals M1, V1 final, plus M2, V2 final. That's all of the momenta. Plural of momentum is momenta, not momentums. Notice M2 initial was 0. V2 final is what I wanted to solve for. So algebraically, this is V2 final is M1 V1 initial minus M1 V1 final over M2. M1 was 0.5 kilograms. V1 initial was 0.450 meters per second minus M1 is still 0.5 kilograms. V1 final was this little number, 0.012 meters per second. M2 was 0.490 kilograms. And this gives me V2 final is 0.45 meters per second. I should have kept another digit, but I didn't, so I don't know what the other digit is. Actually, I can do that real quick. I should have kept the third digit and I didn't, so 0.5, 0.45 times 0.5 or 1, 2 times minus 0.5. So this is 0.447. So they almost exchanged velocities. This one was going 0.45, this one was stopped afterwards, this one's almost stopped, and this one's going almost as fast as the first one was. That's because they had almost the same mass. Anyway, there's our example. So you just, in these conservation momentum problems, add up all the momenta before, set it equal to the sum of all the momenta after, just add up all the M1, the MVs before, add up all the MVs after, set them equal, and solve for whichever part you don't know. It's one of the easier things we'll do this year, and it's really important. So you can practice that in your homework.